Are you tired of building machine learning models only to find they perform poorly in the real world? The problem often isn't your model, but how you're evaluating it. In this guide, we'll dive deep into the ultimate metrics for supervised learning, helping you stop wasting time and start choosing the model every time. For classification tasks, where we predict categories, many beginners start with accuracy. It tells us the proportion of correctly classified instances. While simple, accuracy can be incredibly misleading, especially with imbalanced datasets. Imagine a fraud detection model with 99% accuracy. If only 1% of transactions are fraudulent, simply predicting no fraud for everything achieves that. This is where precision and recall become vital. Precision measures the proportion of positive identifications that were actually correct, crucial when false positives are costly, like flagging a healthy patient with a serious disease. Recall, on the other hand, measures the proportion of actual positives that were identified correctly, essential when false negatives are critical, such as missing a fraudulent transaction. To strike a balance between precision and recall, we use the F1 score, which is their harmonic mean. It's particularly useful when you need a good blend of both. For a more comprehensive understanding of classifier performance across various thresholds, the receiver operating characteristic area under the curve, or ROC-AUC, is your go-to. A higher ROC-AUC indicates better separability between classes. Moving to regression tasks, where we predict continuous values, we focus on error metrics. The root mean squared error, or RMSE, is widely used. It measures the average magnitude of the errors and penalizes larger errors more heavily, as they are squared. It's excellent for understanding the typical error size in the same units as your target variable. The mean absolute error, or MAE, provides the average of the absolute differences between predictions and actual values. Unlike RMSE, MAE gives equal weight to all errors, so it's less sensitive to outliers. Finally, R-squared, or the coefficient of determination, explains the proportion of variance in the dependent variable that's predictable from the independent variables. A higher R-squared generally indicates a better fit. Beyond metrics, avoiding common pitfalls is paramount. Overfitting is arguably the most notorious. It occurs when your model learns the training data too well, memorizing noise and specific patterns that don't generalize to new, unseen data. Your model will show excellent performance on training data but fall flat on validation or test sets. Always use a separate validation set and cross-validation to detect it. Another insidious pitfall is data leakage. This happens when information from your test or validation set leaks into your training process. Examples include performing data scaling or feature engineering on the entire dataset splitting, or inadvertently using features that wouldn't be available at prediction time. Data leakage gives an overly optimistic view of your model's performance, leading to disastrous real-world results. Always split your data. Ultimately, choosing the right evaluation metric isn't a one-size-fits-all problem. It depends entirely on your specific problem, the data, and the business or real-world consequences of different types of errors. By understanding these crucial metrics and diligently avoiding pitfalls like overfitting and data leakage, you'll build more robust, reliable models and truly stop wasting time.